Hey there, in this video we're going to continue discussing curve sketching. So I just wanted to do this one example that has a little more of all the things we have discussing. So domain, slant asymptotes, and vertical asymptotes. I don't believe this one has horizontal asymptotes, but we'll go through it and see what the graph looks like based on everything that we've learned. So find your domain first, then any x or y intercepts, then any asymptotes, the intervals where the function is increasing, decreasing, and then where the function is concave up and concave down. So let's start with the domain. So the domain of the function, notice that this function has a denominator, so we know that for domain the denominator can't be 0. So we're going to exclude all the values that make it 0. So x squared minus 1 is 0 when x is 1 and -1. When you factor this, you get x equals -1 or x equals 1. So these are not in the domain of the function. So that means our domain will be minus infinity to minus 1, union minus 1 to 1, and then 1 to infinity. So that's our domain. Now notice that this function can be simplified. X cubed plus 1 can be factored into, using the difference of cubes, we can say that's x plus 1, and then remember our formula, what does it go? How does it go? If you have a cubed plus b cubed, that factors into a plus b, and then a squared minus ab, and then plus b squared. And so here x is our a and 1 is our b, right? 1 is just 1 cube. So x plus 1, right, a plus b, and then you're going to have x squared minus ab, so minus 1 times x, so just minus x, plus b squared, so plus 1 squared. And the bottom, in finding the domain, we see that this factors into x plus 1, x minus 1. So notice that we can cancel this x plus 1 term. Now from the earlier chapters, what does this mean? This means that we have a hole at x equals -1. So notice that this does not change our domain, right? The function is still undefined at this point. What this just means is that our function, right, the f of x equals x cubed plus 1 over x squared minus 1 really looks like the function, let's call it g of x, equals x squared minus x plus 1 over x minus 1, right? But with a hole at x equals -1. We can figure out putting -1 into this function to see what the y value is. So -1 squared is 1 minus a -1, so that'll be plus 1 plus another 1, so 1 plus 1 plus 1, so that'll be 3. So at x equals -1, this will be 3 over -2, so at -3/2. So this has a hole at -1 and -3/2, right? So -1 is still not in the domain of the original function. This is the original because there is a hole. All right, and then the reason that this is going to be helpful is when we take the derivative, it will be easier to take the derivative of this simplified version of the function, because then we don't have to deal with all the taking the derivative here and getting the 3x squared and getting those higher powers. The critical numbers will be the same. Okay, so domain, the next thing is x and y intercepts. So x-intercepts, how do you find them? You set y equal to 0. And so when you set y equal to 0, you're going to have 0 equals x cubed plus 1 over x squared minus 1. And so this is the same function that when we cancel the common term, you have x squared minus x plus 1 over x minus 1. So when is this equal to 0? And this is never 0, right? Two numbers that multiply to -1 not up to 1, so it doesn't factor. And if you try to use the quadratic formula, you're going to have x is minus b, so 1 plus or minus the square root of b squared, which is 1. -1 squared is 1 minus 4ac, so 1 minus 4. So you're going to get a negative number here. So this equals the square root of -3, which is not a real number. So then this has no x-intercepts, because when I set y equal to 0, right, this is f of x is just a fancy name for y. So when I set y equal to 0, we get no real solution. So no x-intercepts. What about y-intercepts? For y-intercepts, we set x equal to 0. So then you're going to have y equals 0 cubed plus 1 over 0 cubed, 0 squared minus 1. So you get 1 over -1, which is -1. So we have a y-intercept at x is 0, y is -1. And these are points, these are coordinates, not intervals. That is the thing sometimes that is confusing, like what is an interval and what is a coordinate. So you just have to go based on context. Okay, so we have our domain, we have our intercepts, and the next step is to find our asymptotes. So are there any vertical asymptotes? And yes, we have, based on the domain, I see that this is undefined when x is -1 and 1, but we already know that there's a hole at x equals -1, but when x is 1, that one doesn't cancel, so x equals 1 is a vertical asymptote. So +1 is a vertical asymptote. What about horizontal asymptotes? For these, we take the limit as x goes to infinity and -infinity of the function. And so as x goes to infinity, notice that this limit is going to go to infinity over infinity. Well, this, and you could do L'Hopital's rule, but you can see that this, the degree on the numerator is higher, so then, and it's odd, so it's going to go to infinity, and then the limit as x goes to -infinity of x cubed plus 1 over x squared minus 1 is going to go to -infinity. And so we have no horizontal asymptotes, but we do have a slant asymptote. How do I recognize that we have a slant asymptote? The power in the numerator is larger. So how do we find it? This is when we do long division. So to find your slant asymptote, do long division, and so I'm going to divide x cubed plus 1 divided by x squared minus 1. So let's set it up. So on the inside here, you're going to have x cubed plus 1, and so you may leave some placeholders because there's some degrees missing, right? The quadratic and the linear term are missing, so I'm just going to leave some placeholders there. And then the divisor goes on the outside. So then we go, what do I multiply x squared by to get x cubed? And that will be x. And so this is why the placeholders are helpful. Normally you will line up by the degree. So x times x squared is x cubed, and x times -1 is minus x. And just like with any division problem, we subtract. So x cubed minus x cubed, that cancels, and minus x, and then there's nothing there, 0x, minus a minus x becomes plus x, and then bring down the 1. And now I can't keep going. My degree on the divisor is now larger, so I can't continue. So that means that x cubed plus 1 over x squared minus 1 is equal to the quotient x plus the remainder, so x plus 1 divided by the divisor. And notice you can simplify this, but as x goes to infinity and -infinity, you're going to be left with, this will go to 0. As x goes to infinity, notice that the degree on the bottom here is larger, so this quantity is going to go to 0, and so you'll be left with x. So then that is our, so that means that we have a slant asymptote at the line y equals x. So whatever the quotient is, that becomes our slant asymptote. So whatever you have up here, so if your long division had something else like x plus 1, x minus 3, that would be your slant asymptote. So let's see, can we already plot part of our graph? So let's see what we have so far. We know that we have a vertical asymptote at x equals positive 1. We have a hole at 0, negative 1. We have no x-intercept, and we have a y-intercept at negative 1. And so we can plot all those things. So let's see, we have a y-intercept at negative 1. So the graph is going to go through there. We have a vertical asymptote at x equals positive 1. So we have a vertical asymptote. We have also our slant asymptote, which is the line y equals x. And we know, remember, we had a hole at negative 1 and what was it, 3/2. So somewhere around here, negative 3/2, which is negative 1.5. So somewhere around here, there is, oops, that will not be an open circle. So you will have something open there. So the graph is gonna somehow do stuff around here. So let's see, and no x-intercepts. So now this is where we have to figure out the increasing and decreasing part. And we can kind of tell just based on the fact that we have no x-intercepts that the graph can't be around here. Usually a graph grows along its asymptote. So if it was over here, the graph will have to somehow go here and then go to that asymptote, but that will mean crossing the x-axis, so it can't be there. Same thing here, right? So it can't go anywhere this way because it will have to then cross the x-axis. So it's probably in here in those little x's. So let's see, let's find the derivative. And to find the derivative, this is when we are going to use the simplified version of the function. We had written the function in this form to be able to see that, to say that, oh, there was a hole there, so let's cancel that out. And then our function, we said x cubed plus 1 or x squared minus 1 looks like this function. So let's find the derivative of that because they're going to have the same critical numbers. And this one will have negative 1 also as its critical number. So let's see. Let's find the derivative of x squared minus x plus 1 over x minus 1. So this is what our function looks like, but let's remember that we have this is also defined at negative 1, so we have a critical number at x equals negative 1 as well. So we have to check that one because the function is undefined there. So let's take the derivative. So the quotient rule, so bottom times the derivative of the top minus the top times the derivative of the bottom, which is just 1 all over the bottom square. Be careful to resist the urge to say, oh, I can cancel those x minus 1s. You can't, right? Because you have that minus there. So simplify. Can we factor anything out? If you can't factor anything out, that's when you go to multiplying everything out. So I'm going to have x minus 1 squared on the bottom. And on the top, when you multiply this, what do we get? You're going to have 2x squared minus x minus 2x plus 1. And then here, 1 times that is just the same thing. So let's just distribute that negative. So minus x squared plus x minus 1. Always remember to put parentheses here. This is where I see the most mistakes, where no parentheses are placed and then the negative is not distributed. And so let's simplify it some more. Combine like terms, 2x squared minus x squared just gives me 1x squared. And then, oh, my x's minus x, those cancel. Oh, and the 1's also cancel, plus 1 and minus 1. So what are we left with? So 2x squared minus x squared, that's 1x squared, and then just minus 2x over x minus 1 squared, which you can factor out 1x out of here, and you're left with x minus 2 over x minus 1 squared. So our critical numbers then, when you set this equal to 0, this is 0 when the numerator is 0, so when x is 0 and when x is 2, and it's undefined when x is 1, and remember when x is negative 1 as well, because that is where the function has a hole in the graph. So let's put those in here. So I'm going to put negative 1 and then 0, 1, and 2. So we have 4 critical numbers, and you're testing the derivative. So f prime, and we're trying to see what is the function doing. So pick a test point. So we can pick something on this side. So you can say x equals negative 2, for example, and plug it in. So let's see. Let me put my little, this is undefined. The derivative is 0 here, and it's undefined at those 2 places. So when x is negative 2, here's our derivative. So you're going to have negative times a negative. Notice that the bottom is square, so this is always positive. So you're going to have here negative times a negative over positive, so that will be positive. So the derivative is positive, which means that the function is increasing. And then pick another test point. So let's say x equals something between negative 1 and 0. So let's say negative 1/2. And plug it in. Let me copy my derivative here so I can see it. Okay, so now that I can see it there, x is negative 1/2, so I'm still going to have negative times negative 1/2 minus 2, that's still negative, over the bottom is always positive. So you're going to have positive again. So the function is increasing, and then at negative 1 it continues to increase. So the derivative here is positive, so between negative 1 and 0 it continues to increase. So that's interesting there. And then let's see, 0 and between 0 and 1, so let's pick another test point. So let's say x equals positive 0.5 in this case, and plug it in. Positive 0.5, that will be positive. 0.5 minus 2, that will be negative, over, that's always positive. So you'll get negative. So the derivative is negative there, which means the function is decreasing. So notice that now you have a local max at 0. And let's pick another test point. Between 1 and 2, you can pick x equals 1.5. And so positive 1.5, that's positive. Positive 1.5 minus 2, that's negative, over the bottom is always positive, so you get negative again. Derivative is negative, means the function is decreasing. And then something bigger than 2, let's pick 4. So when x is positive 4, you're going to have positive 4, so that's positive. Positive 4 minus 2, that's positive, and the bottom is always positive. So you get positive, which means that the function is increasing. So at 2 you get a local min, because you go from decreasing to increasing. So from here, can we graph the function? So you'll have a local max at 0, and remember when x is 0, what happens when x is 0? That was our y-intercept. We set x equal to 0, and 0 happens to be a critical number, so you have a local max at 0, negative 1. So going back to our graph here, so notice that now that means we have a local max here. So that makes sense that the function is increasing, and when you get to the little open circle, it continues to increase, and then you hit your max, and then it decreases. So, and remember, we grow along an asymptote. So then this is increasing, is undefined there, and then continues to increase, and then it decreases. And then what happens on the other side of 1? So our critical numbers are negative 1, 0, 1. 1 is an asymptote. So then it decreases between 1 and 2. At 2, you hit a local min, and then it goes back to increasing. So it will be good to find what is the value when x is 2, since that's when you're going to have a local min. So if you go here to 2, right, what is the y value? So let's plug it in. So when x equals 2, what is y going to be? Y is going to be then 2 squared minus 2 plus 1 over 2 minus 1. And what is that? 4 minus 2 is 2 plus 1 is 3 over 1. So that's 3. So at 2, 3, I'm just going to say it's right there. You're going to have your local min. And so that means that our graph decreases along the asymptote, and then you hit your local min, and then you go back up. You start to increase following still the asymptote. So then this is what our graph will look like. Hopefully yours will look a little better than mine, but that is an idea of what the graph will look like. Now we still have to check concavity. So at this point, it looks like it's concave down all the way through here and concave up all over here. So I'm imagining we're only going to get one critical number, which will be, or inflection point, which will be 1, and that's where it changes concavity. But it's not really an inflection point because 1 is not defined. So when you find your second derivative, I'm not going to go through the math for it, but when you find the second derivative, your second derivative for f of x will be just 2 over x minus 1. So this will be your second derivative, which now notice that it makes sense that you only have one critical number. So x equals 1 makes the second derivative undefined. And so when you test this, so you'll have -1. So that you'll go, okay, so this is where the second derivative is undefined. What is the function doing? So plug in a value, plus 1. Plug in 0, for example. So when x is 0, notice that 2 over 0 minus 1 will be negative. Second derivative is negative, means the function is concave down. And then something bigger than 1, plug in 3, right? 2 over 3 minus 1 is 2 over 2, which is positive, which means that the second derivative is positive. And when the second derivative is positive, that means the function is concave up. And so that matches what we had found here, just based on increasing and decreasing. You can, as I've mentioned in previous videos, you can graph pretty much the function by up to increasing, decreasing. You can figure out how it looks, but it's always a good idea to make sure that your concavity matches what you have drawn. So in this case, I kind of drew it based on what I knew, but now my concavity does match it. And in fact, we probably should have checked that -1, because -1 will be also a critical number, but it will be concave down in that area. So okay, so this example kind of had everything. It had a hole in the graph, it had a slant asymptote, it had a vertical asymptote, and different things going on. So yeah, email me if you have any questions.